Good afternoon, everybody, or morning, depending on when you're watching this video. My name is Aengus. I'm a medical doctor, so I'm currently working at the Medical AI Directors at Harrison.AI. We build AI tools for clinicians to help empower them develop better, faster, and cheaper healthcare for the mass. So today, it's my pleasure to talk to you about AI from AI to bedside, a journey in taking this innovative technology from ideas to the bedside and serving patients. So it's probably useful to take a step back and think about the evolution of AI in healthcare. So artificial intelligence, AI, is a very old concept. This has been around since the 50s. And AI is loosely defined as any computing system that can perform cognitive tasks, so tasks that resemble human intelligence. And because of this broad concept, even very simple system such as a rule-based system that look at the heart rate if it's under 50 beats per minute, called a NUS. This can actually be considered an AI system. And in the 50s, this dominate the fields where people trying to write extensive rules to describe very highly complex cognitive tasks. And as you can imagine, this is not a very scalable approach because if we cannot write down on papers how to do certain tasks, it is very difficult to program a software to perform these tasks in this way. Because of that, we didn't make tremendous progress in the field. And in the 80s, a different kind of approach to solve intelligence has emerged called machine learning, which focusing at instead of teaching the algorithm to do exactly what we want it to do, we actually teach the algorithm how to learn. And by feeding it a large amount of data, we can teach this system to perform highly sophisticated tasks without explicitly telling it how to do so. For example, by collecting blood tests, vital sign monitoring, one can build a system that statistically learn to predict whether or not the patient will have sepsis based on past observation. And this field has developed a lot, able to build sophisticated statistical model to estimate this unlikely event. But once again, the limitation of these algorithms is the expressiveness. When the problem become highly complex, these statistical models start to break down and is unable to find meaningful patterns. And recently, in the 2010s, a new wave of artificial intelligence approach has arrived called deep learning, which is basically statistical model, but on steroid, where we have powerful neural network algorithm that mimic the way the human brain works and is able to leverage tremendous amount of data that arise within the past couple of decades and able to extract and learn powerful representation, such as directly at pixel level data from images. So now we can solve issues like what are the chances that the patient have pneumothorax or pneumonia on a chest X-ray. And this has given rise to a host of potential solution in healthcare. It all starts with a single most important data set in the entire deep learning field. It's called ImageNet. It is a data set of millions of day-to-day objects that's collected on the internet and has been labeled by human for which images contain what objects, such as car, coffee cups, donuts, that kind of objects. And using this data set, a competition was created. It's called the ImageNet competition, where every year researchers trying to build algorithms trying to predict what object is in these images at the highest accuracy possible and trying to reduce the error in doing so. As you can see, in the 2010 and 11, the error rate was anywhere between 28 to 26, meaning that one every 4 images would contain an error in prediction. And because of this was not very useful in any practical application other than research. But magically, something happened in 2012 where there was a big performance jump from 26 to 16. And this is called the AlexNet moment, where researchers for the very first time is able to build an algorithms that able to reduce the error rate in ImageNet without hand coding the features, what is in the image, such as cat have pointy ears, or car has 4 tires and that kind of thing. It's learned directly from the data using massive amount of compute. And ever since, the progress has been tremendous in driving down the error rate of this visual recognition system using artificial intelligence. And in 2015, it's the very first time we passed the human performance in doing the same task. So we clearly has transitioned from the age of discovery, where it's primarily about computer vision research, into the age of implementation, where we can take these computer vision system that is superhuman and apply that into meaningful problems in healthcare and in solving it meaningfully. If I'm able to summarize what AI is, it is this. AI lower the cost of prediction. We've seen this before in other technologies, such as the computer chips. The reduction in cost of silicon chips able to build these computing system at low cost. And because of this, everything we do today surround around computer chips. Even turning on a microwave involves a microtransistor that's more powerful than a machine that sent man to the moon. And the fact that we can do this recording today over the internet is all due to the reduction in cost of arithmetic through this computing system. What would happen when the prediction itself has a reduction in price? We know that when something becomes cheaper, we do more of it and we can solve more problems with it. So in healthcare, we are surrounded by predictions. You may not know it, but when we walk into a clinic, the nurses make prediction about how sick we are and whether or not we need to stay or go home. When we take a chest x-ray, a radiologist need to make a visual predictions on whether or not there are pathologies. When a clinician read a medical report, they need to predict whether or not those patterns of symptoms and signs and medication you take result in a risk of further complications or disease. And every day, our doctors looking at blood tests, vital sign, and past history in order to make a determination about the likelihood of deterioration, such as sepsis or myocardial infarction in this example. So medicine is surrounded by predictions, and the reduction in cost for prediction using artificial intelligence is an incredibly exciting thing. But how do we harness this technology and turn it from research into the bedside? At Harrison, we had the fortunate partnership with Virtus Health, one of the largest IVF providers in the world, in developing technology we call IV. That's allowed the embryologist to select the best embryo possible for transfer. And we would like to share with you today the 8 steps that we went through in converting these very novel ideas into a practical application benefiting patients around the world. The very first step is always to ask the right questions. And in IVF, one of the most important questions is which embryo will have the best chance of create a pregnancy. Because if we can do this, we can reduce the time to pregnancy by prioritizing the embryo with highest viability first. Here's the videos, a time-lapse videos of human embryo growing inside Vitrolife time-lapse incubator for 5 days. And the problem we're trying to solve is to look at this video and estimate the chance that each of these 12 embryos will result in a pregnancy. The second step is always about collecting large amount of data. We all have heard that data is the new oil. But I would contest, label data is a new oil. Because without the label, without the outcome, there's no way to teach these algorithms about the nuances of embryo development. That's why this 10,000 embryo data set has been labeled by the pregnancy outcome as determined by fetal heart pregnancy. And that is the signal that we use to teach this algorithm to learn for itself what video is correlated with the best pregnancy potential. The fourth step is to handcraft the best AI algorithms using the state-of-the-art architecture. Unlike what may have been taught in traditional media, this algorithm is highly tuned and is highly customized to serve the purpose. For example, we have developed algorithms that look at the entire time-lapse video sequence, which examine every hours of embryo development throughout the 5-day process. This is much superior comparing to analyzing the image at the very last day of the 5-day development cycle, because we get much richer data about how the embryo developed instead of just how it looked at the very end. And most importantly, making this algorithm explainable. Here's a visualization of IV algorithms, focusing on different sections of the video. The red being the area that contribute the most to the viability of the embryo, and the blue is the area that contributes to the non-viability of the embryo. And as you can see, without ever teaching the algorithm about embryo development, the algorithm figure out for itself different sections, highlighting the molar compaction here, for example, as a key developmental event. We also need a lot of compute. So we got this supercomputer that we built, and we trained it on the 10,000 embryo dataset, and is able to reach expert level performance in predicting the pregnancy outcome as determined by fetal heart pregnancy. We have papers published in Human Reproduction that detail this work, but it's important to highlight that these solutions are inherently medical device and require rigorous validation and highest level of evidence before they can go into clinical practice. The final step of the journey is to put it in the hand of clinicians and integrate seamlessly to their day-to-day workflow so that they can take advantage of this technology and support their work. IV has been deployed over the last 12 months in many clinics across Australia, and we are very proud of this. Soon, this algorithm will be available through Vitrolife in every device. And recently, Harrison has partnered with Vitrolife with the development of IDA-Score, the next generation algorithms that is the follow-up work to IV, which much more power, expressiveness, and train on much richer, diverse data set of data. I would be happy to pass it on to Jen later to talk about this. And if we do everything right, this is what we are rewarded with. This is the articles in Courier Mail that features a baby that was born with the assistance of the IV algorithm in selecting the best possible embryo for this mom. Here's the 8th step again. We need to ask the right question, gather a big amount of data, label this data effectively and quickly, handcraft the best AI algorithms and architectures using state-of-the-art methods and best practice engineering, train the AI algorithms on a supercomputer and highly tune them for best discriminative power, rigorous scientific validations and regulatory approval, and as well as seamless deployment into existing workflow, and have a good partners to distribute that so that can be in the hands of clinicians all over the world. Before I pass it on to Jen to present how the score was developed, I just want to leave you with a framework on how to pass the complexities of bringing an AI solution from ideas to bedside. It is an idea taken out of a book called Prediction Machine, which is adapted toward the use in healthcare. There are 6 questions that each of us have to ask before we can apply an AI solution into a problem in healthcare. The first row deal with the ideas itself and the validity, while the second row deal with the technical challenges with building these algorithms. The first box called prediction. What is it that we are trying to predict? In the case of IV, we're trying to predict whether an embryo one transfer will lead to a successful pregnancy with fetal heartbeat at 6 weeks. The judgment here is that IVF is a highly emotional and financially expensive endeavor for couples. So we don't want them to have repeated cycle. We want them to have the best chance of pregnancy as early as possible. The actions, once we predict the best possible embryo, is for the embryologist and the gynecologist to transfer the best embryo for the patient, resulting in a successful pregnancy. And the outcome that we're looking for is the accuracy of these algorithms in predicting that outcome. To develop these algorithms, we need an input data set of time-lapse videos in the time-lapse incubator for 5 days. And the training data is the pregnancy outcome that come along with those training video. It's also important to know that these algorithms are not static, and feedback data is required once the algorithm is deployed, so the algorithm can continue to learn and improve based on real-world statistics. And finally, the value here is that we reduce the emotional and financial burden of IVF patients while improving health equity and making the traditional subjective process much more objective, which is the goal that we're looking to achieve. Next, I would like to pass it on to Jen to present the IDA score and developments of the next generation algorithms. Thank you so much for your time.